Hello, welcome once more to my channel. In this particular lecture series, we are going to look at some problems involving momentum. So the first problem we have here has to do with a lawn tennis player who strikes a ball against a vertical wall. The mass of the ball is about 0.50 kg. The velocity of the ball is 25 meters per second, and the ball was using this velocity to strike the wall and bounces back with that same velocity. So the question now is, what is the change in momentum of the ball during the impact? So looking at this problem, for us to know the change in momentum, we have to know the initial momentum and the final momentum. Then the change in momentum will have to be the final momentum minus the initial momentum. So in this case, we say let the momentum before impact be P1. The momentum before impact is P1, which is our initial momentum. While the momentum after impact, let's take it as P2, that is our final momentum. So the change in momentum will be final momentum, which is P2, minus initial momentum, which is P1. And so we have P1 is M1V1, which is 0.5 kg times 25 meter per second. That gives us 12.5 kilogram meter per second, which is the initial momentum. Now, the same ball striking that wall, having the same mass, bounces back with the same velocity. So the momentum after impact, we have the same magnitude as the momentum before impact, but in this case it will be in the opposite direction since it's bouncing off the wall. So therefore P2 will be negative 12.5 kilogram meter per second. So from there you can now get the change in momentum during impact, and that will be minus 12.5 kg, which is P2, minus P1, and P1 is 12.5 kg. So eventually that gives us minus 25 kilogram meter per second. So having done with question 1, let us look at question 2. For question 2, we are going to look at, okay, we have questions 2 and 3 here. Question 2 says compute the velocity of recoil of a 7 kg rifle that fires a 0.05 kg bullet at a speed of 450 meters per second. Now, we'll treat this system as an isolated system. And since the system is an isolated system, momentum is conserved. If momentum is conserved, that implies that the momentum before impact, that's the initial momentum, is equal to the momentum after impact. So initial momentum is equal to final momentum. So we have the equation on the screen. P is used to represent momentum. So the initial momentum is P1, the final momentum is P2. So this equation represents, this is the initial momentum of both the bullet and the rifle, and this is the final momentum of both the bullet and the rifle. So we have the parameters given. We simply substitute all these into equation 1. We are assuming the rifle to be the first object and the bullet to be the second object. So M1 corresponds to the mass of the rifle, M2 corresponds to the mass of the bullet. And then for each of them, the rifle is assumed to be in a state of rest. The bullet is also assumed to be in a state of rest. So if that is the case, then both of them will have initial velocities of 0 meter per second. So that's why we have V1I is 0 meter per second, V2I is 0 meter per second. So simply substitute this into the expression, and solving further gives us a final velocity of minus 3.21 meter per second. This is the velocity of recoil of the rifle. Why is there a negative sign? It implies that the rifle is moving in the opposite direction of the bullet. And coming to question 3, we have a bomb placed initially at rest on a flat surface, suddenly explodes, and upon the explosion, pieces of the bomb were scattered in different directions. Explain how momentum is conserved in this scenario. Quite simple. The bomb was initially at rest. If the bomb is at rest, then it implies that its velocity is 0. If the velocity is 0 and momentum is mass and product of mass and velocity, then of course momentum will be 0. And because the system is regarded as an isolated system, there are no external forces acting on the system. Hence, we say that linear momentum is conserved for such a system. So upon the explosion, what happens is that the pieces of this bomb are flung in different directions. And so when we take the vector sum of the individual momenta of these bomb pieces, then we add up to 0. So this is how momentum is conserved in this scenario. And we take a last question. So here we have a pitcher applies a constant force on a baseball. The mass of the baseball is 0.25 kg. And that ball receives a constant force from a pitcher over a distance of 1.2 meters. When released, the ball travels at a speed of 26 meters per second. So here we are to find the force acting on the ball, the change in momentum, and the time it takes the force to act on the ball. What's the mass of the baseball? Is 0.25 kg. The distance covered is 1.2 meters. The initial velocity of this ball is 0 meter per second, and when released, it gets to a final speed of 26 meters per second. How do we get the force acting on this ball? We use F is equal to ma, Newton's second law of motion. But here we don't have any value for the acceleration of the ball. So we have to use the equations of motion, one of the equations of motion, to find the acceleration of the ball. Most appropriate equation of motion here is v squared equal to u squared plus 2as. S is the distance covered. So we simply do a little substitution into this equation and solve further, simplify further, and that gives us an acceleration of 2281.7 meter per second square. So from this, we can now get the value for the force acting on the ball. So the force gives us from F equal to ma, the mass is 0.25 kg, and acceleration is 281.7 meter per second square. So by the time we multiply, we are going to arrive at 70.4 Newton. Second question there says we should find the change in momentum of the ball. What's the change in momentum? Mass times change in velocity, which is m into final velocity minus initial velocity. In our problem, the initial velocity is 0 meter per second and the final velocity is 26 meter per second. So when we do a simple substitution and multiplying further, that gives us change in momentum to be around 6.5 kilogram meter per second. And then the time it takes the force to act on the ball. Recall that the impulse of a force is equal to the momentum of the body. So F times T, which is impulse, is equal to mass times change in momentum. So we just do a simple rearrangement of this equation so that T is equal to mdv over F, and mdv is the change in momentum which we got from part B. So that is 6.5 kilogram meter per second divided by force, which we got from part A, 70.4 Newton, but the Newton is equivalent to 1 kilogram meter per second square. So when we solve further, we're going to arrive at 0.09233 seconds, which approximates to 0.092 seconds to 3 decimal places. So it takes 0.092 seconds for the force to act on the ball. So we'll come to the end of this particular series on momentum. Next lecture, we have to cover elastic and inelastic collision. Remember to like my video, comment,